Hello everybody, getting ready to do lesson 7.4 part 1 classwork for pre-calculus math today. And for today's lesson we got part 1 here, 7.4, matrices and systems of equations. Write matrices, identify their dimensions, perform elementary row operations on matrices. Use matrices in Gaussian elimination to solve systems of linear equations. You got 18 points here to go into your notebook, students. Have your notebooks ready or your notebook guides ready. And then 42 points here will go onto your class worksheet for part 1. But first we have a bell work. Teachers, students, we have today's bell work here is solve the inequality and graph the solution on a real number line for both of these here. So that is your task today, students. Teachers, give your students 5-6 minutes for that. Turn off the video or pause the video or pause the PowerPoint, and we'll be back in 5-6 minutes. Okay, so the solutions for today's bell work for inequalities up here: solve the inequality and graph the solution on a real number line. Here's our number lines here for inequalities. So for this one, 102, x plus 10 quantity, absolute value of this quantity here, greater than or equal to negative 3 is true for all x, since any quantity inside absolute value will be greater than or equal to 0. So it'd definitely be greater than negative 3. So it'd be true for all x here, would be the solution for that, and it'd just be an open number line that would express true for all x. And then down here for 104, this can be factored down into 3x times quantity x plus 4 greater than 0. And then our critical numbers here are negative 4. We used the zero product property. And then and then for here be 0 here for 3x, so 0, negative 4. And then checking the 3 intervals, you obtain x is less than negative 4, so it'll be on this side of negative 4 over here, and x will be greater than 0, so it'll be anything greater than 0 and then less than negative 4 would make this a true statement. And here would be the graph of the solution set for this inequality here. Okay, moving into today's lesson with a notebook entry here, page 1. We have, in this section, you will study a streamlining technique for solving systems of linear equations. This technique involves the use of a rectangular array of real numbers called a matrix. The plural of matrix is matrices. A definition of a matrix would be if m and n are positive integers, then an m times n, or read m by m, matrix is a rectangular array. So if m and n are positive integers, then m times n, or m by n, matrix is a rectangular array. So what does that have to do? Here is a rectangular array here. Column 1, column 2, column 3, column n, row 1, 2, and 3, then row m here. So this is where we get our m times n here. So this would be A1, 1, column 1, row 1, column 1, row 2, column 3, row 1, or rather row 3, column 1, row 3, column 2, row 1, column 1, row 2, column 1, etc. And then row m, column 1 in this situation here. So row 1, column 3, etc., etc. In which each entry aij of the matrix is a real number. An m times n matrix has m rows and n columns. So the rows are m and then the columns are n. The entry in the ith row and jth column is denoted by the double subscript notation a to the ij. So row would be first and column would be second in your way that you would name these things. For instance, the entry A23 is the entry in the second row. So row A2, second row, then third column. A matrix having m rows and n columns is said to be of dimension m times n. If m equals n, then the matrix is a square of the dimension m times n, or m times n, or n times n. For a square matrix, the entries A11, A22, A33 are the main diagonal entries. So by default, these will be your diagonals here, A22, A33 of a matrix. Okay, let's try one now. So in example 1, dimension of a matrix, determine the dimension of each matrix. So we have here A is 2. So the matrix has 1 row and 1 column. So here's a matrix right here. This is technically a matrix just with a number 2 in there. The dimension of the matrix will be a 1 by 1. So here now for B it'll be 1, -3, 0, and 1/2. So that situation, it has 1 row, you have 1 row and 4 columns. So you have 1 row, then 4 columns here. The dimension will be a 1 by 4, so this will be a 1 by 4. And then for C, now we get a little bit more going on here. The matrix has 2 rows, we got 2 rows and then 2 columns. The dimension will be a 2 by 2. And then for D here, we have this situation here. And then this matrix has 3 rows. We got 3 rows and then 2 columns. The dimension would be a 3 by 2. That'd be a 3 by 2. And then this situation here will be for E. This matrix has 3 rows and 1 column. So the dimension of the matrix will be 3 by 1. This will be a 3 by 1. Okay, determine the dimension of this matrix here and determine this one here, students. So for this one here, it has 3 rows and 1 column, so it's a 3 by 1. What would this be, students? Before your students, before you put it up, I mean, quiz your students in the classroom. Don't just throw these over. Since the matrix has 3 rows, 1, 2, 3, and 3 columns, it is a 3 by 3. So this would be a 3 by 3 here. A matrix derived from a system of linear equations, each written in standard form, with a constant term on the right, is the augmented matrix of the system. Moreover, the matrix derived from the coefficients of the system, but not including the constant terms, is the coefficient matrix of the system. The matrix derived from the constant, and stop here, from the constant system. So here's a matrix derived from the constant system. So this would be x, y, and z, and then here is out here are your coefficients, and then this one is missing a y, so it just has a 2x and minus 4z, and then here's your constants out here. And then this will be an augmented matrix where you drop your variables and you just have your coefficients here. And then this is supposed to provide another symbol for your equal sign out here. And then here are your constants out here. And then a coefficient matrix would not include n equals here. They wouldn't be equations, they would just be a matrix here that shows a coefficient of a system. And then we have a constant matrix here. It just has constants here. There's not meant to have any variables that are involved with that. Okay, another notebook entry here. So note that the use of 0 for the missing coefficient of y variable in the third equation. So this is like a placeholder here in a third equation. And also note the fourth column of constant terms here. We have this symbol here is the augmented matrix. The optional dotted line in the augmented matrix helps to separate the coefficients of the linear system from the constant terms. So this just, I guess it's just a separation here for your constants. And when forming either the coefficient matrix or the augmented matrix of a system, you should begin by vertically aligning the variables in the equations and using zeros for any missing coefficients of the variable. So basically it's just like a placeholder there for that. Let's try one now. Writing an augmented matrix. Write the augmented matrix for this system here. So how will we go about doing that? What is the dimension of the augmented matrix is the first question you ask yourself. Begin by writing the linear system and aligning the variables. So here it is. Here we're aligning our variables here. We don't have an x in this row here, so we move that one over here. So this is a linear system. Everything's lined up by columns by its designation. When we do that, next use coefficients and constant terms as the matrix entries. It includes zeros for the coefficients of the missing variables. So when we do that, we end up with this. This would be an augmented matrix. Once you go to this step, and then your next step into an augmented matrix will be here, row 1, 2, and 3. You have zeros here, you have a 0 here, you have 0 up there, and then here's your constants out here, and then these are your coefficients there for this system here. The augmented matrix has 3 rows and 4 columns, so it is a 3 by 4 matrix. The notation r to the nth is used to designate each row in the matrix, row 1, 2, and 3. For instance, row 1 is represented by R1, R subscript 1. Okay, let's try one here. Write the augmented matrix for the system of linear equations. What is the dimension of the augmented matrix? So, question. Here is your augmented matrix. When everything's lined up here, you don't have a z here, so you have a 0 there. And then this just separates this part of your matrix from your constants out here. They don't say it's an equal sign, but it's just a separator. So when we have that, our dimension here is we have 3 rows, and then we have 4 columns here. So it would be a 3 by 4. This will be a 3 by 4. Elementary row operations. So in section 7.3, you study 3 operations that can be used on a system of linear equations to produce an equivalent system. So 1, interchange 2 equations. 2, multiply one of the equations by a non-zero constant. And then 3, add a multiple of one equation to another equation. So these are ways that you start these kinds of functions, these kinds of operations to produce an equivalent system here. These are some strategies here that you use for that. In matrix terminology, these 3 operations. Okay, so moving on from that, from row operations, an elementary row operation on an augmented matrix of a given system of linear equations produces a new augmented matrix corresponding to a new but equivalent system of linear equations. 2 matrices are row equivalent when one can be obtained from the other by a sequence of elementary row operations. So here is the basis that we use to do elementary row operations for matrices. Number 1, interchange 2 rows. Number 2, multiply one of the rows by a non-zero constant. And then 3, add a multiple of one row to another row. So that's all allowable to do row operations. Although elementary row operations are simple to perform, they involve a lot of arithmetic. Because it is easy to make a mistake, you should get in the habit of noting the elementary row operations performed in each step so that you can go back and check your work. Example 3 demonstrates the elementary row operations described above. On to example 3 now, that will go into elementary row operations. interchange first and second rows of the original matrix. Here's our original matrix. Here's first row, second row. So new row equivalent matrix. So we just flipped rows here. So now row 1 is down here, row 2 is up on top, like this. So we can totally do that to solve a system of equations. Okay, so B, multiply the first row of the original matrix by 1/2. So here's the original. We're going to multiply this by 1/2. So when we do that, our 1/2 times our original row 1 will give us this new row 1. So 1/2 of 2 of -4, 6, and -2 will give us this now. This is our new row 1. And then C, add -2 times the first row of the original matrix to the third row. So now we're going to add -2 times first row. We're going to add that to our third row after we do our multiplication. So here is our new row equivalent matrix. So it's -2 times row 1, and then we're going to add that to row 3 down here. And then this is our new row 3 down here, 0, -3, 13, and -8. And then this is what we started with. This was the original row 3. So that is totally, okay for row operations. So let's try to solve one now. In exercises 23 to 26, identify the elementary row operation performed to obtain the new row equivalent matrix. So here is our original, and then here is our new row equivalent matrix over here. Same thing down here for 26. So what happened between here and here is the question. So what happened between here and here? So for up here for 25, what happened was we interchanged rows in 1 and 2. So we just flipped this one up here, and then this one came down here. That's what this is. This has been differed by interchanging rows 1 and 2. And then down here we have 5 times row 1 added to row 3. So row 3 here is changed. So we multiplied row 1 times 5, and then we added that to row 3. And then here is our new row 3 after that operation. And that is 7.4 part 1 of classwork. If you need a new classwork sheet or any other course materials, here's my email. So thank you very much.